All right, so I'm Mike McKerns, and this is basically why HPC in Python is broken and how to fix it. I'm going to focus on Python object serialization primarily, but actually I want to thank Peter. He covered a lot of the same things that I was going to cover, so I can go through them a little faster. So my first project in Python was really a HPC project, and I started in about 2003. On these two big projects, ASC and the dance projects, both were very large academic projects, produced parallel computing frameworks. I primarily built an MPI parallel map implementation to do launch code, Python code on cluster schedulers, Torque, Slurm, etc. I built Pathos, which does SSH tunneling, copying, execution. Also has a parallel map and pipe execution, so it's nice programming model type work. They both follow the multiprocessing interface with pools and etc. And then we also worked on a target of predictive science analytics, which was Mystic. I have a poster out there on Mystic. We built flexible optimizers that were built for built to leverage parallel computing. The problem was when we finally got to the end of the projects and we put both of them together, it didn't work. And it didn't work because, well, surprise, Python sucks at HPC. Basically, it appears to be perfect at first. It does a lot of things like dynamic lazy evaluation, weakly typed language. So it does a lot of things right. But really, when it goes down to it, it relies on this global interpreter lock, the GIL. And that makes the code execution be thread locked. Really, all the GIL is it's an integer, a read-only integer in the PyC layer that it gets set when main starts, and then Python can't change it. And frame objects, which where the execution stack live, always refer to the GIL, and it basically checks to see that each object that's built on a frame object that refers to that stack, which is basically a mini language to evolve code into other objects and then other objects and other objects beyond that. It checks that number, and if it has a different number, it doesn't work. So that's the real trap, and there's no way to get that number. You can't like rebuild. You can rebuild a frame object. Surprisingly, I know how to rebuild one, but I can't get that same number back. I can't get the GIL number back because there's no access to it in Python. So it does some of these nice things. It empowers the language with yield, iterators, generators, and these nice stack objects, all the way up to when you write things like closures and you do code object, basically have a code object inside of a closure that then gets ported to a function object and evaluated dynamically. So it does a lot of cool things in Python. But basically, it is one of the detractors for parallel computing. So people do some workarounds. They do multiprocessing and not threading. We've seen things like Python has no GIL, and C types, basically you can go in and access shared memory in C, the PyC layer. So that's some nice workarounds, but really the major issue is anything that is an object in Python that leverages the stack is not really serializable. If you look at the majority of the language, it's not serializable. Most Python objects aren't serializable, which means they can't be shipped off to another processor. So any of you who've tried parallel computing pretty much and tried, you pickle the object, you use map, even in multiprocessing, it just dies for almost everything. It generally fails on most of the interactively defined objects where we pickle by reference, and also most of the primarily utilized language constructs. So that really has stunted the growth of Python and HPC. So don't be discouraged. Python gives you a few things you can do, right? You can use C types, and actually I've built a few object serialization techniques that allow you to go down and leverage C types to get around the GIL, and there's a few things that use source extraction to extract the source code from an object and then put that source code, re-inject it through code compilation into another object. But primarily, there's partial language serialization where you can do things like copy read and reduce and get state to basically teach Python how to serialize an object. And actually, both of those two things combined over the course of several years, I started this package DIL in 2009, have basically given me almost all full language serialization for Python. So basically, I can cover almost the entire language. Some of the frame objects I still have trouble with. Some of the objects that are based on the frame, I have a plan for working on iterators. And I'm actually to the point where I have some, I know iterators are solved in 3.4, and that's because the access was given to a particular pyc call that allows you to do it. And that's exactly, they did it through C types, and that's exactly what I would do right there to continue with iterators and generators and some of the stack tools. But it's basically Stackless does this, but Stackless is not Python. So if we follow what Stackless does, we can actually cover the rest of the language. But DIL covers all of the basic constructs in Python that designers work in, closures, multiple closures, decorators, you name it, it pretty much does it. And we can save classes by reference or save classes by definition, which means you can actually pickle the class code into the object. So when the class definition changes, you can still get your class instances back. So there's a lot of different things. You can pickle the whole interpreter session, save it, restart the interpreter session. You can send that interpreter session to another machine and restart the session there. So that right there was an empowering piece of technology built over a couple years. And the unfortunate part is it still didn't work in that most code used pickle, and I couldn't touch pickle's code, right? So I wanted to use it in multiprocessing. I wanted to use it in other code. And I basically couldn't because I had DIL and it was pickle, and pickle was part of the language. So what I did is I did a nice bootstrap trick, which pulled all of the everything that pickle knows, everything that DIL knows into pickle, and it still didn't work. And that still didn't work because people have their own conflicting workarounds for pickle, and they use cpickle, which is not in Python. So then I forked multiprocessing, MPI for Py, parallel Python, RPyC, PyCUDA. This was a while ago in 2009. And then stuff starts to work. And you actually get normal coding like you would do in Python with the same language constructs using the concept of map and pipe like multiprocessing has and pool. And you can do things like map a function onto jobs that are running at the national labs and in parallel. And so we have continued to do pathos and pyina, HPC stuff, and develop it over the time. We have like nested heterogeneous maps that are available. We have things like running the maps not just from main, but actually from interpreted code, asynchronous, iterative, non-blocking maps and pipes. So there's still a lot to do. I want to leverage, I had PyCUDA, but I want to do OpenCL, and I want to do better use of shared memory. But it's used actually by me and some others, folks, to do very simple things like this. You know, this is mapping on Slurm, where I say MPI map of my model over some range, and then that one is across a socket layer. And so we have things like you can nest those together because DIL allows me to do that, and I can make hierarchical parallel maps and basically explore system design very quickly with programming models. So I have this other package that I use now to share state between machines. So this is a fairly new, designed this year, Klepto. It's got the idea talking to Gael over several years on JobLib and DIL and whatnot. And it basically has a unified API for caching and archiving, and it allows different archive strategies. You can rely on memory, on a file system, on a database, leverage NumPy internals. It does interpolation, cache interpolation, rounding, things like kriging I'm working on. I actually have an implementation that does HDF as a backend, but the idea is to abstract the communication between two resources through a database table And it basically is augmented by pickling because I can save anything. And so we used it to basically build this big global optimizer that does statistics, some very large problems. So we do things like, please see my poster out there. We have very large parallel computing optimization algorithms, and you can see some of the code out there on the poster. We've done some science, big statistical science that runs on these big machines. There's a big 20-hour, 2,000-way MPI parallel job that we then ran on 4 machines at 2,000 petaflops, all in a single calculation to do parameter sensitivity, and that was over the course of 8 days. So that was all managed by basically, the magic was just being able to serialize the objects and then do a simple map and map reduce. And we're now in a project that is trying to do exascale computing, and it's got a bunch of industry partners, and we're doing the programming models and statistics part, but it's a very large project. So I'll wrap up. It's a huge amount of scope to be able to change Python to a real parallel computing language. There's a lot left to do. There's a lot of, I can't do it all myself. It actually needs to be a bigger community effort. I would love to see DIL be part of the Python language, and I would love to see more emphasis go on to programming models, parallel distributed computing. So the code's on GitHub, and please don't settle for the state of Python HPC as it is. Step in. There's a lot of good packages like other ones besides mine. If you'd like to contribute, please do. Thank you.